Hello, welcome back here at DevNation Tech Talk. Today, I'm your host. My name is Natalia Vinta. I'm a developer advocate here in Red Hat. I'm very happy to have two special guests today talking about integrating Loom in Quarkus. Hello, Clement and Arthur. How are you?
Good. Thank you, Natalie. So yeah, today we are very happy to present our work around Loom and how to integrate Loom in Quarkus. What are the different approaches we have tried, the different things we have attempted, our failures, where we are and where we are heading. So we are going to talk about all this. I expect some slides about Loom, but also some demos because we already have some good integration of Loom in Quarkus, and we are going to demonstrate that. So, but before that, let's introduce myself real quick. So my name is Clement Escoffier. I'm Senior Principal Software Engineer at Red Hat, and I'm doing a lot of reactive things, including Quarkus, a bit of Vertex, and things like that. And today I'm very happy to co-present with Arthur.
Hi, everyone. Thank you for having me here. I'm currently a PhD student at Red Hat, and on my engineering time, it's like split, half research, half engineering. It's not half, it's like 80-20. I'm working with Clement and Julien on Quarkus and Loom stuff.
Fantastic. It's very cool. We have this research program where the student can do the research and also work on open source engineering. That's super cool. And Clement, Arthur, I'm looking forward to hear from you about this talk. So I know you have some slides. Clement, you were right. Here we usually do live demos, and I know you are a very super fan of live demos. So we're very happy to have you both here.
Yeah, so yes, expect live demos. I'm going to do live coding. I'm going to do even live debugging. So imagine that. Unfortunately, this session is a little bit shorter to the original one, so there are some demos that we have dropped. But if you are interested, you can ping us. That's our Twitter handle. And if you want to see the slides on PDF, you can download them on this URL you have on the bottom right of your screen. So Natalie, should we be starting?
Yes. Let me share the slide, and I take also the opportunity to ask the audience if you have any question, please send in the chat. After the talk and the slide, we're gonna bring the question to our guest today.
All right, so let's get this started. And so the first thing to understand Loom is to understand actually what a thread is. So let's start with a thread about threads. So it sounds basic, but it's always good to remind everyone about how things works. Your program is always running inside a process. That is a memory space. However, your code runs on a process thread, sometimes called OS thread. And I will use these two terms indifferently in this presentation. So process thread or OS thread. What is key is that those process threads are managed by the operating systems. By default, there is one, the one calling the entry point of your applications. In Java, it's often called named, but your framework or your program can spawn new process threads. The operating systems is in charge of maintaining the list of threads and giving them access to what actually executes your program, the CPU. So all the scheduling is done by the operating system. So remember that, that's pretty important. In Java, there is two execution models. The first one, the widely more popular one that I call imperative, is actually leading to a very simple development model. So how it works, while you do web app, something very simple, and you get an HTTP request or anything, and then you associate one thread to that request, and the processing of that request will be handled from A to Z by these threads. So the request arrives, you take a worker thread from a thread pool, okay, that thread will handle it, you start your processing, and because we are doing distributed systems, call them microservices, call them serverless, maybe you are doing a data-centric things and you need to integrate with a database or data lake or whatever, then you are going to do an I/O. the model that is proposed by the imperative execution model is actually very simple. You do the I/O and you wait for the response. You wait until the I/O completes. So your program waits, so the thread is in a blocked state. When the I/O completes, you can continue processing and so on and so on. One of the problems of this model is that if you want to handle concurrent users or concurrent requests, you need multiple threads, but you have a limited amount of threads because each thread costs memory. We are going to talk about that later. And so having too many threads will eat too many memories. So you have a strong limit there. The competitive model is what we call the reactive execution model. In that model, which is much, much closer to the operating system and how it works, it's a model which is also applying the mechanical sympathy principles. And the idea here is to have a very few amount of threads that we will call I/O threads, generally also called event loops. And then that thread will manage many, many requests concurrently. So how it works? Well, you receive a request, you start the processing, and as soon as the processing cannot make progress anymore because it needs to do some I/O, again, calling another service, doing some database interaction or whatever, it is going to schedule this I/O in the operating system and associate to this I/O a continuation. What's a continuation? A continuation is a block of code that is going to be invoked when the I/O is complete. So basically, you do that, you do the scheduling, you pass the continuation, the thread is released, so we are not blocked, so you can handle another request on the very same thread, and so on. When the I/O completes and the thread is available, boom, you call the continuations. One of the key aspects of this is that your continuation and your request are called on the very same thread. So this model is very, very efficient. However, you need to pass this I/O, this continuation, do the scheduling of the I/O, so it leads to more complicated code. You can do that with callbacks, you can do that with reactive programming, you can do that with a coroutine. It's always a little bit more complicated than the imperative development model. And there is a golden rule. You should never, ever block this I/O thread. Why? Because if you start blocking, waiting for an I/O to complete, then you cannot handle another request. You block the thread. And because you have a very few number of these threads, generally it's 2 times the number of CPUs. So if you block them, nothing will happen until the I/O completes. So the whole model collapses. Remember this rule, we will come back to that rules a little bit later in this presentation. So basically what we have the imperative model, very simple to develop with, very simple to reason about, sequential execution, things are great. However, it's expensive. It's around 1 megabyte per thread plus 10 microseconds for the switching between threads. So it has a concurrency limit. Reactive, well, it's a more complex development model, let's be clear. But it's a lot more resource efficient. It can handle a lot more concurrency. It uses a lot less threads, and it works very, very well when you have constrained environments such as containers or small cloud machines. So, right, but what about Loom? Arthur, can you tell us more about Loom?
Yeah, thank you, Clement. So indeed, as Clement just told you, the aim of Loom is to reunite both of the best of both worlds, right? And not only is it better for the development model when you actually develop your program, but in terms of debugging and performance analysis, the tooling of the JDK and JVM has been thought about the abstraction of thread. So even using those tools, you're going to have a better experience with Loom than you had with callbacks invoked in the event loop. So this is basically what's going to happen with the virtual thread of Loom, right? You will have this thing called the carry thread, which is the good old process/OS thread. And on top of it are going to be mounted virtual threads. So as you can see, you have 3 of them on this figure. And when the first one, the virtual thread number 1, is going to perform a blocking code, a blocking call, what's going to happen is that it's going to hit some library in the JDK, some code in the JDK that's going to unmount it from the carrier thread. And hence the carrier thread is going to be able to do something else while the operation is actually being accomplished. And when the operation is going to complete, the virtual thread will be able to be remounted while it stopped its execution on top of the carrier thread. Now, an interesting thing that happens with Loom is that they implement work stealing. This is something that is quite efficient for the kind of load you have when you have a remote service, a web server, for example. It's the idea of you don't have just one carrier thread, right? You're going to have a set of carrier threads, and each of them are going to be, a carrier for different virtual threads. So when one of them will be starving and it will not have enough tasks to run, it's going to steal things from another carrier thread in order to, balance the traffic. This is something that you can already see in the Go scheduler basically from the beginning, I think, of Go, and that is implemented in Loom. So one observation that we could make right now is that the model of the carrier thread on top of which are going to be mounted virtual threads might remind us a bit the model of the event loop, right, on top of which are going to be executed different requests. But now the main difference is that the virtual threads in the case of Loom can be suspended. As Clement told you, when you develop in a reactive way with event loops and callbacks and stuff, you need to separate your continuations. So, right, one continuation is going to be a function, a runnable, a callable, and then they're going to be called, and they need to execute from A to Z before being finished. A virtual thread can have several continuations in the same space, and it's going to be unmounted, suspended, and mounted back onto the carrier thread. So the development model is way simple, and all that we said. And so now the time has come to interrogate how this magic works. And the figure is a bit complicated, but as you'll see, it's pretty simple. You have your carrier thread on the bottom, a poller. It's basically an abstraction to talk about the interactions between your application, the JVM, and the operating system. So what's going to happen is that your carrier is actually running the virtual thread number 2 at the beginning of our figure. The virtual thread number 2 is going to perform a blocking call. It's going to be parked. So somewhere in the JDK, there is this spark function that is going to be hit. And what this spark function does basically is that it's going to take the stack of your virtual thread. It's going to store it in memory. So we are actually reifying the execution of the program as a data structure that we can put in memory in the heap of the JVM. Once it's been done, we are going to register a future call to unpark, right? The method that is going to be used to resume the execution of the virtual thread. And then once this call is registered, then we're going to be able to unmount the virtual thread, allowing the carrier thread to process another one. So it's going to process the virtual thread number 3, then the virtual thread number 1. And as you can see, during the execution of the virtual thread number 1, there is something that happened either on the network or on the disk that's going to, say to the poller, right, an event happened in the operating system. I know you were interested in this event. Do what you have to do. And since we registered this call to unpark, the poller is going to call the unpark method for the virtual thread number 3 in our situation, and it's going to submit, its continuation back to the carrier thread. So when a virtual thread is unparked, it doesn't begin executing right away. It is actually submitted into the work queue of a carrier thread to be executed sometime in the future. Hopefully, since everything's supposed to go fast, near in the future.
So, well, that's great, Jose, but it's time for us to show some code and to see how it's working. So let's switch to do some code now. So the first thing you need to do is to use JDK, which provide Loom. So fortunately, Oracle provide previews of the JDK 19, which include Loom. We will give you the URL at the end of this talk. And then I'm going to use a version of Quarkus, which has Loom inside. This is something that is going to be mainstream relatively soon, but right now you still need to build it yourself. And I'm going to start my application in dev mode. So if you did Quarkus already, you recognize
Clement,
that.
Which version of Quarkus will contain this?
Probably 2.10, so the one we are going to release in June.
Okay,
I cannot commit on that, but yeah, it's probably going to be this. The pull request is already open. It's a little bit complex, so getting reviews is taking time, and we need to do all the curation work on the pull request, but it's going to be there. Okay, cool. And no worries, you will still be able to use Quarkus on previous Java version. We detect everything for you, so no problem about that.
Cool.
So my Quarkus application has been started in dev mode, so that's great. So nothing changed about that. But what do I have in terms of application? Well, it's a very simple quote application that I call Fortune. I have a Fortune repository okay, which deal with my database and retrieve fortunes that are stored in my database. My database is already started and gets fortunes inside. I have a random and I got a logger, so nothing very interesting. So the first thing I'm going to do is to call that method here, which answer to the slash blocking path. So it's going to, well, do some log, we will see why, get all the quotes from the database. I received a list of fortune and pick a random one. Very simple. So if I call this method, so I go there, let me see here, yeah, it's called that, so it works. I can get my quotes from my database. Everything is working. If I go back to my console, I can see that this method is called on a worker thread, executor thread 0. So because here we just use one because yeah, it's available. So every time we reuse the same one. So the second thing we can do with Quarkus, inside the same code, inside the same application again, is to use some reactive call. So here, instead of returning a fortune, I'm returning a uni of fortune. So it's an asynchronous type that say, I will get a fortune, but I don't know when. But until that, the thread is released. So here the code is a little bit more complex because I need to do a find all async. So I'm querying the database using an asynchronous driver. And when the database answered, it will call the map function that say, well, when you have that response, pick one. So we see that even on this code, it's very simple. There is a bit of complexity. So if I call this here, it works. And now if I go back to the console, this time we see that we are called on event loops. So this time we are called on these IO threads that we can't block. So how does Quarkus decide that? It's based on the signatures, it's based on the annotations. We are going to have a slide about that in a few minutes. But what about Loom? So again, this Quarkus version is Loom ready. So I'm going to copy this code here. I'm going to paste that here. I will call that Loom over GDBC because it's a blocking access to my database. So it's using GDBC. I will call that Loom GDBC. And the only thing I need to do is just say, hey, Quarkus, can you run that on a virtual thread? That's it. So now I do this. I go back to my UI here. I refresh, and I can call using Loom. And now, if we look at the log, we see that we are called on virtual threads. And one key thing here is that those virtual threads are so cheap to create that we don't pool anymore. We don't have a thread pool anymore. We can just create millions of them. So that's pretty cool here because we have a clear isolation of the processing of our request. One request, one thread, no reuse. So very, very nice. So basically, we just added one annotation and we're good. So let's go back to the slide to try to explain a little bit more how things work under the hood. So basically, what we have is this. Blocking, fine. That's what you do most of the time. You return a regular type. It's a blocking access to the database. You're called on a worker thread. On the other side, we have reactive. You are called on the IO thread, but you need to use Mutiny or another supported asynchronous construct. And in the middle, you have Loom. So we take the code from blocking. We just add one annotation. So we really, what Hasu said, a very simple development model. So how it works, Quarkus has a build time principle, and this build time principle lets us decide at build time which strategy we need to use for each endpoint. So basically, the heuristics are based on the signatures and annotation. If you are using a reactive types or your endpoint is annotated with at non-blocking annotation, we are going to call you on one of these few event loops we have. If you are using an imperative types or you have annotated your method with add blocking, you are working on a limited number of worker threads. And if you are using run on virtual thread, well, then we have we have a dynamic number of carry threads, that's a fork join, and then we create one new virtual thread per request, and in an unpooled fashion. So that's pretty cool, pretty simple, one annotation, and everything is great. Everything is great, Arthur?
Well, kind of, but not exactly right. The Loom team has been pretty honest on this matter since the beginning of the Loom project. There are some occasions where parking doesn't happen the way you want it to happen, right? So what's going to happen basically is that they have a fallback method. So if there is a problem with either storing the execution in memory or unmounting the virtual thread to the carrier thread, they're going to call park on carrier. So what's going to happen is that the virtual thread is going to be pinned to the carrier thread, and both are going to be blocked. So this is the old model, right? The OS is going to preempt the thread that performed the blocking code and put it in a waiting queue, and then once the operation is complete, it's the operating system that's going to put it back in the run queue of the operating system. This is what we call the pinning phenomenon. And this is something that is pretty bad, because if it happens, then your application is as good as the previous model, the blocking model was. So it shouldn't happen, right? That's what Clement said.
Yeah, so that should not happen, right? And let's see this in action just right now. So this is my code, nothing changed. And what I'm going to do is that I'm going to debug that code. Run, attach the process. This is my process here. And so here is my debugger. And I already have a breakpoint. So it's a logging breakpoint. I'm not suspending the execution. I just want to log something. And I'm going to log when this park on carrier thread method is invoked, which means that we are pinning the carrier thread. So let's see what's happening if I go back here and I refresh and I do Loom over JDBC a few times. If we go back here, what we're seeing is that we are actually parking the carrier thread, which is pretty bad, because basically that means blocking our event loops. It's more or less the same thing. As Arthur said, it's kind of a reactive model. So if we block that, it's not as it's something we want to avoid. So what about that, Arthur? So what can we do? Oops. Let me go back to the slide first.
Yeah.
Here.
So when I said that the team had been honest from the beginning, I mean that they actually gave us, the occasions where this phenomenon of pinning could happen. The first one is if you call actually native code that's going to call back Java code that's going to perform a blocking operation. If you do so, they're not going to be able to unmount the virtual thread and to remount it later on the platform thread. There was a university by Rémi Forax and José Pomar who explained why, and it has to do with how the variables, are stored in terms of memory in C, and yeah, you can go back to their university to see why it can't work. But the thing is that it can't work, right? You can't unmount and remount the virtual thread. In synchronized block, you also will pin, right? If you perform a blocking call in a synchronized block, then you are going to pin the virtual thread to the carrier thread and put it all. And the most surprising thing we encountered was with the JDBC driver. If you are doing a DB transaction using the JDBC driver, the transaction will pin the virtual thread to the carrier thread. And it doesn't just pin it, at the start or at the end of the transaction to do some, I don't know, state modification or something. It actually pins it during the entire transaction. So if you have a delay of several hundreds of milliseconds between your database and your service, then during several hundreds of milliseconds, your thread will be blocked, actually. And that's why, of course, a lot of the Java ecosystem would need a rewrite to make it compliant with this, avoiding actually pinning the virtual thread to the carrier thread.
So the question is, how can we use Loom today in a safe way? So avoiding or reducing the amount of pinning. So remember that Quarkus at its core has a reactive engine, which is based on Vertex and things like that, and Netty, but that's details here. What's important is that because of this, it exposed a lot of reactive API, and those reactive APIs are exposed using the Mutiny model. Mutiny is a reactive programming library that has been designed a few years ago, but when we designed it, Loom was already starting kind of thing. So we already did the kickoff call about Loom. So we were looking at what was happening and so on. And when we designed Mutiny, I said, well, something that would be cool is to provide some way to block, which doesn't make any sense in terms of reactive, but block in a way that Loom will not block. So basically, in Mutiny, you have constructs that are going to wait for a result, wait for next items, if you are doing streams, but without blocking the carrier thread. So basically, from this code here, you have on the top, which is bad because it's blocking, it's pinning the carrier thread. We are going to do this. And this is not going to block the carrier thread. So let me demonstrate that real quick. So I'm going to copy this code again. I love copying. I will call that Loom. I will call that Loom. All right. And instead of doing the GDBC call, which is pinning the carrier thread, I'm going to do find all async and await. So, and something to understand is that for the whole set of reactive APIs we have in Quarkus, there are the method, which return a uni or multi, and a variant of the method which is suffixed with and await. And these and await method are awaiting for the results, but in a way that it's Loom compliant, it's Loom friendly. So basically with this, you can just keep your same code, more or less. The only thing to say is, okay, fine, I'm going to use an asynchronous driver using this reactive API, but my code doesn't change. I'm still writing blocking code. This is going to be executed before this, and this is that. So very sequential and so on. And now if I call this, write that here, I do here, and if I clear it, just to be sure that we don't have it, empty. So we are not pinning the carrier thread, which is exactly what we want here. So while it's not perfect, it's a way to use Loom today, reducing the pinning phenomenon. So let's go back to the slide to explain how it works under the hood. So basically what we have, so we have those reactive clients, which, because they are reactive and because they work that way, are executing everything on the event loop. So we have our carrier thread, we have our code, which is a virtual thread, so that's a log and then so on. So this virtual thread is going to use the asynchronous client with a Mutiny API, and that is going to send an event to the event loop to execute that code. So that code is going to interact with the database and so on. And because it's reactive, it's going to release the thread immediately. You in the virtual thread, you don't really care because you have used the and await method. So you are just waiting for the result. It's coming, but you are not blocking the carrier thread. You are just suspending the execution of this virtual thread. When the database finally answers, and again, that can take seconds, even minutes, depending on the query or what you want to do, then it sends an event to the carrier thread, which will unpack our virtual thread, and our virtual thread will be remounted and will continue exactly where we stopped. So just after the and await, and so we can have the result of our interactions. So, of course, if you see that model, you say, hey, can't we have our carrier thread and our event loop be just one? And well, that's actually something that Arthurs have tried to do, and he will explain how was that week, Arthur? That was probably a very good week, right?
Yeah, so basically we're trying to do this by merging the event loop and the carrier thread. So basically we had the event loop that also had to perform a task of a carrier. So some of the tasks it had to run were just runnables and callables, and some tasks it had to run was actually carrying the execution of the virtual thread. The problem is that you can't really do that. Actually, you can do it, but it's super risky and it might cause deadlocks. And we actually had a deadlock because of system.out.println line, because the current implementation of system.out.println uses locks, and when you share locks between your carrier thread and your virtual threads, then they might both be in the same queue, and then they both need the other one to get the lock in order to, unlock the situation. But it's something that, it's a deadlock, so they both wait for each other. So we basically discarded this model, and I think this is also why the API that gave the ability to the user to use a customized, custom executor, to choose how to dispatch virtual threads on top of carrier threads, has been removed from being a public API. Now you can't really customize what you want to do. They do it for you in order to avoid this kind of situation, I guess.
So back to the plan A, which was actually plan B, because that what Arthur explained to us just now was actually our plan A. But so we have those event loops and those carrier threads. So what about the performance cost of such kind of model? So for this, we have done a benchmark, but because we didn't want to implement yet another benchmark, which will be probably broken as most of the benchmark we are seeing. So we are reused Tech Empower. So Tech Empower is a neutral benchmark where you can find a lot of different language and frameworks competing. It has multiple scenarios, so going from a very simple hello world to something a little bit more complicated, like the one we are going to see, which is Fortune. And they run that scenarios both on bare metal, so on Buffy machines, and on the cloud, so on something a lot smaller. So it's very interesting for us to have the two type of environments. What we have implemented is a variant of the Fortune scenario. So the Fortune scenario by default is just fetching all the rows from a database, quotes. So it's very similar to what we just showed you. The difference is that in the scenario, you need to add a quote to the return list, sort the list, so it creates some CPU things. And in our variant, we are returning the list as a JSON object. So the official version of Fortune is producing an HTML page using a server-side template engine, but it has no interest in our case, so we simplified it to do the JSON mapping instead. So, of course, thanks to with that scenarios in mind, we have implemented 3 times. So the blocking using worker thread, the reactive using IO thread, and Loom using the carrier threads, and 1 virtual thread per request. We have done many different environments, but today we are going to look at one which is very interesting for us, which is more or less what we are seeing when we run containers. So half a CPU, 512 megabytes of RAM. Yes, it's small, but that's what we are seeing these days. We are doing some variants in terms of concurrency from 1,200 requests per second to 4,400. Something to keep in mind is that we have added artificial latency between your application and the database. Because it's, well, let's be clear, there is no environment where your database and your application are running on the same machine. So generally, it's a separated machine. It's network calls. Network calls have latency, so we wanted to have that latency. And actually, here in these numbers, we have 0.2 seconds. We also have tried with 0.5, and the results are quite different. So the latency is impacting a lot. Well, that makes sense. But it's really impacting a lot the concurrency of our application. We are measuring a lot of things, such as the response time, the throughput, and the CPU and resident state size. The resident state size is the amount of RAM that your application is using. So it's not only the heap, it's really all the memory that your application is consuming. So let's talk about the results, Arthur.
Yeah, thanks. So what you can see is 3 lines, right? The red one is Quarkus Reactive. The dark blue one is Quarkus Loom using virtual thread, and the light blue is Quarkus blocking. Quarkus blocking, you can quickly expect the maximum level of concurrency because you just take the number of workers you have in your worker pool. Here it's 500 for 500 megabytes of RAM, and you divide it by the duration of each request, which is here basically 200 milliseconds. So you have 500 times 5, and you have 2500. That's basically the maximum number of requests you can support. And as you can see, Loom is way better than Quarkus blocking, right? You can go up to 3,500 requests, although Quarkus Reactive is even better because you can go up to 400 and 200 something. Throughput, the right figure, it looks like Loom is really falling apart after its critical point, but we don't really know what happens with Quarkus Reactive later on, and it might be the case that it also falls apart. So it's not an advantage for, it can go further, but once it reached its critical point, it's not better than Loom, right? We just don't know what happens. So those were the numbers for latency and throughput, and now we need to also care about the efficiency in terms of managing the resources. And what we can see is that the memory consumption of Loom is actually quite heavy, right? For low concurrency levels, it's basically on par with Quarkus Reactive, right? Just a bit above it. But once you get to 2,000 and something requests per second, it basically increases super fast to get even heavier than Quarkus blocking. Now, one quick thing we have to add is that the actual weight of the virtual threads and the continuation in the heap are not that big. It's mostly data structures that are generated by Quarkus and Netty because of the integration of Loom in Quarkus that have this impact on the memory consumption. So it's something that maybe we'll be able to work on in the future.
So just to conclude, so we had the imperative, which has a limit concurrency. We have seen that on the benchmark. We have reactive, which is very, very concurrent and efficient. And we have Loom, which is in the middle. The development model, yes, it's simple. However, we need to be aware that to use it safely, we may have to use this dance with this event loop and asynchronous client, because if you don't, then you may ping the carrier thread and then everything fall out. So if you do that, you have a quite good concurrency. It's not as good as reactive, but it really makes a lot of sense for all those applications that want to go a little bit further than blocking without being completely an API gateway with very high level of concurrency. However, today, the resource efficiency is not really there. So it comes from the Netty integration. There is also things in Loom too. So things will probably improve in the future, but at the moment, it's what we have. So the famous last words. So the first thing is that right now, you can already use what we have shown today with any databases that we support in the reactive client the reactive database client we have in Quarkus. That include relational database such as Oracle, Postgres, MySQL, and so on, but also NoSQL database like Redis, Mongo, and so on. You can use any network client such as a REST client, gRPC, GraphQL, and so on, Plain Engine, emails, and so on. On the roadmap, we have things like messaging, because typically the model doesn't really apply well to things like Kafka. There is so far I didn't find a good way of doing it. We want to handle more servers, typically a gRPC, but we are in the process of changing the gRPC server, so let's do that once we have the new one. And lots of tuning, especially to reduce resources, the resource usage. How to use Loom in Quarkus today? Well, you go on jdk.java.net/Loom and you download JDK previews. That's going to be Java 19 with Loom support. Then you go to this pull request and you build it. It has been rebased yesterday by Azure, so you have a very latest Quarkus, and we plan that for Quarkus 2.10. Then you just use @run on virtual thread, and you're good. If you run it with run on virtual thread on a non-Loom JDK, not a problem. We just fall back to blocking, which is a lot safer than falling back to reactive, where you will block. So you can just start using run on virtual thread, and you're good. If you have Loom, you will use it. If you don't, you will use blocking. Finally, so Loom promises to be simple, efficient, and concurrent. It's a pretty young project. At the moment, unfortunately, the ecosystem is not ready, and it will take a few months, probably years, for the ecosystem to evolve and to reduce the pinning. At the moment, it's very, very dangerous. There is lots of conditions where pinning can happen, and it can really break the model. we can use what we did in Quarkus Loom with this netty things and this dance with the event loop. It's a compromise, so it's a trade-off, but it works, and it works relatively well. We have seen the concurrency is already quite good. So if we want to conclude right now, simple we have it. Concurrent, it's not that bad, but efficient, there is still progress we can do to make it even more efficient and really become cloud native, because right now this resource efficiency may be a problem to really use in environment where you want to achieve a very high deployment density. That's all we have for you today. So again, you can download the slides on this URL here. If you have more questions about Quarkus, you can go to quarkus.io, ping us on Zulip. And if you never use Zulip, it's like Slack with a very high level of concurrency. So you will love it. And of course, you can see many videos about Quarkus and everything we do around it on YouTube. That's all we have. And I believe, because Natalie pinged me, that we have a few questions.
Yes, the talk it's very interesting, Clement, Arthur. I have also lots of questions, but I can't because we have lots of questions from the audience. So let's go through them. I don't know if you can read them. So there's Eric that say, does the random virtual thread annotation have to appear only in JAXF RS resource classes, or can it be any method or any CDI bin?
So hello, Eric. So at the moment, we are focused only on REST Reactive. We wanted to start small on something we control everything. We are going to add that to everywhere. So, but we wanted to start on something we do understand well. So we did that here. That's actually why I'm trying to do it with messaging with Kafka and things like that.
Okay, thanks. Then there's Passy saying, isn't this pinning with synchronized going to be a temporary problem?
Yes. According to the Loom team, it's going to be fixed. Maybe not in the first release, Java 19, but probably in the future they shall fix it. Sorry for forgetting to say it.
So that's for synchronized. It's not the case for native. Native seems to be an impossible problem, at least for now.
Okay,
but yes, synchronized, yes.
Thanks. Another question for random virtual thread annotation. Is there some way of throttling the number of virtual threads? In the past, the thread pool provided a crude throttling mechanism, but now something else is needed. This is Kay asking.
Yeah, this is a very good. This is actually a very interesting answer, and we try to answer it, during the implementation phase of Quarkus Loom. And the thing is that before, in 2021, you could actually choose what executor you use to dispatch your virtual threads among your carrier threads. So you could implement some logic inside of your executor that would delay, that would throttle, how virtual threads would consume task queues and how carrier threads would consume run queues to execute virtual threads. Now that is not something that you can do as a user. However, in the Quarkus Loom implementation, we actually use reflectivity, right? We use reflection in order to be able to fetch private inner code at runtime, and so we can do stuff here. But we haven't really decided on an API that would let the user customize what we do with our code in order to create an executor.
So there is also a lot of works, and this Loom works has opened a lot of questions in terms of fault tolerance. What it means in terms of fault tolerance, in terms of hotbound concurrency. Because yeah, sure, if we create millions of if we receive millions of requests and we create millions of virtual threads, and all those virtual threads call the very same service, which is a very old legacy service, yeah, something bad is going to happen. So, and we want to avoid that. So we have discussion with fault tolerance team, so Ladislav and friends, to try to see what can be done. So rate limiting, bulkhead, and things like that. So we will see. It's clearly a new paradigm, a new execution paradigm. So we need to rethink even these kind of things.
And just to piggyback on what you said, there is also some effort with structured concurrency that is being done directly by the Loom team and by public contributors that are trying to give an API to the users in order to create a whole bunch of virtual threads and control timeout, maybe bulkhead, and so they have a whole bunch of structures that you could directly apply to your virtual threads in order to have more control over them as a group and not as individual threads or individual requests. So you might check it out. Yeah, it's structure concurrency, Loom, and you'll find.
Yeah, I'm not a big fan of what they have done there yet, but it's probably going to be improved. I'm not sure it's going to be included in the first preview of Loom. I need to check.
Okay,
I think
thanks.
feedback would be good.
We have last two questions. So why not switching to a language that is built from the ground with strong concurrency primitives instead of reinventing the wheel on Java? This is solid from Twitch.
Yeah, and that's actually a very, very good question. So there are many languages that have this built in. Let's just Go, and also mention Go, but we can even mention REST, which has await things, and they have done a very interesting work in something called Tokyo.rs, which is a network toolkit using this. Node.js, it's not a language, but and so on. However, we need a solution for Java because there is plenty of workload in Java today and tomorrow. So what do we do? Do we stay in that model, but blocking is too limited? Reactive will work, yes, sure, but require a little bit more expertise in terms of writing and things like that. So Loom is going to provide the right solution to be for the middle ground, let's say. And I think it's an important step for the Java community. Now, there is other things on top of Java that you can already use today. We didn't mention them, but typically Kotlin coroutine. They work. They're very well integrated in Quarkus. So if you are looking for a different model, you can already use Kotlin coroutine. Well, if you understand Kotlin, of course. But yeah, they are very, very interesting. And we actually didn't really compare the perf with the Kotlin coroutine. It's something I've asked Arthur to look once he sleeps a couple of hours. So tomorrow.
I guess Arthur has lots of work to do, no?
Yeah, I'm a pro at delegating things to Arthur.
Yeah, I think I'm a pro of throttling the task I'm given to. So
I've seen some stickers there. Maybe you are collecting all the tasks that Clement sent you in the stickers in the post-it. Yeah. So thanks, everyone. We have one last question. We are extra time, but this talk was very interesting and lots of traction and questions. Last question: given performance issues are fixed, is there any reason why we wouldn't want to annotate every resource with random virtual thread annotation by Jonathan?
So that's an amazing question, and actually, it's what will happen eventually. The problem is that as of today, there is too much risk of pinning, and we consider it as a safer approach to have these annotations. There is another thing too. If you do I/O expensive tasks like projecting things or computing taxes or whatever, it's a tax season in France at this moment, so we do that a lot. So really CPU intensive. While it's not blocking because of I/O, it's going to take a lot of time because it's complex and it's going to use your CPU. You can do that on a worker thread. It's not great, but we did that a lot because we have many of them, so that's fine. If you do that on a virtual thread, it's not going to really pin the carrier thread, but because it's not pinning, but it's going to avoid any other virtual thread to be executed at that time. So there is a few things we still need to learn. So because of all this and because of the trade-off and the dangers, we have decided to go for the safest approach first. And in a few years, maybe in a few months, we will see how fast the Java ecosystem can evolve. We will make run on virtual thread automatic as soon as we realize that you are on a Loom, Loom aware, Loom friendly, or Loom powered JDK. Yeah, I don't know. Loom something JDK.
Very cool, very cool. So thank you, Clement and Arthur. This was really, really interesting. I'm looking forward to check the slide that you shared. If you like to follow Clement and Arthur, you can share your Twitter handle there on Twitter if you'd like to follow them. The DevNation Tech Talk come back on June the 2nd with Daniel Hall. We're going to talk about event-driven autoscaling through KEDA and Knative integration. Another very cool session. And thank you everyone for attending today. And thank you, Clement, thank you, Arthur, and see you soon. Bye.
Thank you very much
for having us.
See you.